let's talk about the branch point. So these are singularity, and like this one doesn't actually go. It could go to goes to infinity at z equals zero, but it could also not go to infinity, or the limit doesn't exist actually when z equals zero. But uh, for another kinds of singularity is it may or may not be singular at that point. It is called branch point. The f is a multi-value function, right? Then obviously at any point can have multi-value, but to determine whether which one is the branch point, you just look for any point, look for a loop around it. To consider the loop is not doing integration, just calculating f going around a certain loop around a certain point. Right? Give any given point, look for its neighborhood and going around it. If going around a loop, you're going back to the same function, same value, then that is not a branch point. Although this is a multi-value function, but if you just move around a little loop around that point and you go back to the same value, it's not a branch point. So a branch point would be a point when you go around it, per close to it, going around it, no matter how close to it, going around it, you get a different value. Then it's a branch point. Okay, have we talked about the branch point before? The, like c to the one half function, right? Obviously, you know the branch point. Obvious, quite obvious. Which one is the branch point? Going around which point will give you different value. One half, yeah. Square root function, one half. We talked about that before. So you just like if you use a polar coordinate r and theta, right? C to the one half is r e and theta to the one half, right? And you go around any point, if you see if this point, if you just going around it just a little bit, away from this point, what is the theta value? So just if you go around a certain point, no, what is theta? For this, the z is r e theta. Any point z, this is z. If I just found a little loop going around it, uh, what is theta? So theta, you start with any value, right? Start with, say, here, whatever the value is. Theta will decrease, and then increase, and then decrease, right? Does that change any point? Does theta change after going around? No, it doesn't. Right? Because uh, you just follow the theta. Theta is just like the angle it makes with the real axis, right? Follow the point. This is theta decrease. When you increase it, theta or increase back. When you increase, theta increase. But after this, theta is get to the maximum point, and you go back, theta decrease. When you're going around a loop, what does theta change? No, theta doesn't change, right? So it's not a branch point. Any point that is away from the origin. So for this function obviously, you will choose zero as your point to consider. You're going around a loop, right? Start with theta zero, then keep increasing, you go to 2 pi. And that will increase theta by 2 pi, but this function is now to the 1 half e to I theta over 2. If theta increased by 2 pi, then this exponential function increased by e to the I pi, which is a negative sign. It completely changed the sign, change the negative sign. So then the value is not the same anymore. Okay, you change from say start from zero, then it's a positive value. It goes from 0 to 2 pi, then you get a negative sign. Okay, so the branch point is zero, and in many cases, z to the fractional power or a real number, not integer power, that would be a branch point of zero also. Okay, and these are branch points that if there's an order of branch points, I think it's also called the order. Right? And sometimes this terminology is difficult to remember. So basically, the z to the 1/2 has two branches. You go around once, you get the 2 pi. Go around twice, you get 4 pi. But then the 4 pi divided by 2 is 2 pi, which is just one. So you only have two branches for this one. So likewise, here to the 1/3, you have three branches and so on. But some function will have infinite many branches, like z to the real power. This is not any rational power mu. Then it will have infinitely many powers. Right? No matter how many theta, how many n times 2 pi increase, that will not go back to one. E to the I mu theta over 2. Right? Increase whatever, so no 2. E to the I mu theta. Right? That one, theta increased by 2 pi times n integer. And that is not 1 because mu is a real number. Okay, so another infinite function with infinite branch, we talked about that before, right? So x is log c of the log c minus c, we define it slightly more general, right? Then f f c, right? Where is the branch point for this one? This here, right? Yeah, c equals 0 is your branch point. Just like what we considered before. So only going around c sub 0 will increase the phase of this function. The phase will increase because whatever this c minus c 0 equals to some magnitude times the angle. When you take the log of this, you get log of this plus I theta. So theta, if you keep increasing it, it will just that imaginary part will keep increasing. Okay, so that is also a infinite have infinite branch. Okay, now for branch point, when we want to do integration, usually we want to restrict it back to one branch. We want to cut the complex plane so that it's single value. And it's not always, but it's most often we want to do that. You don't want to keep going around, keep going to different branches and to do your integration. Okay. In many cases, we want to keep the function as single value. See, again, if you have a c to the 1/2, this is a branch point. And this is not singular. This is an example that the branch point is not singular. Singular means that it's not infinity. It's at 0, it's not infinity. And then you can connect the branch point to anywhere that go to infinity. The reason going to infinity is that you totally separate the complex plane. You cannot just stop somewhere because beyond that you still have the ambiguity. Right? You want to go to infinity so that you restrict your range of theta. Say in this case theta Because if you call this theta 0, the theta will be from here, negative value of this to positive value to a value plus 2 pi. Right? Anywhere is fine. And there are cases that you don't want to go to negative real axis or positive real axis or imaginary axis. There will be cases that you want to cut it somewhere with a finite angle. And, but in many cases, you uh, seems to be more convenient to cut it along real axis or imaginary axis. And the idea is after you cut it, you define your function over a single branch. So you decide what the range, what the domain now. You define your function to make it single value. In this case, you cut it to negative infinity, a negative real axis. Then obviously this any point is C have a theta. So now basically the branch cut. This is a branch cut. The branch cut is restricted your value of theta, not minus pi to pi. This is minus pi. When you get close to the branch cut, it's minus pi. They go around to above it become pi. So that after you have a branch cut, you define your range of your how you define your variable. If you cut it to the real axis, then obviously that theta will be, you can start from 0. The theta will be greater than 0, less than 2 pi. It's 0 going around 2 pi. Right? So that branch cut. Well, if you only have one branch point that use that would be fine. Anywhere would be fine. Depends on your question, which way you cut it becomes convenient. If you have more than one branch cut, branch point, if you have more than one branch, I think your textbook has an example. This is the function c plus 1, a c squared minus, instead of the c to the 1/2, you have a c squared minus 1 to the 1/2. So that is just c minus 1 to the 1/2, c plus 1 to the 1/2. Okay, so that would be, there are two branch points, right? You can see that. Where are the two? Minus 1 and 1, right? Everyone can see that. It's important, right? If you're doing an integral, if you're integram, you want to identify singularity, you identify where are the branch points. And you know, what about 1 minus 1? Well, then again, the branch cut is arbitrary. You can do whatever you want. You can likewise say like minus 1 going to infinity, 1 goes to infinity. That is fine also. Uh, and in that case, because it's you have this 1/2 factor, just 1/2 factor, it becomes a special case that if you a define appropriately, then that is only become multi-value. You cause a line connecting the two branch points, so you can cut it. You can say you connect the two branch points. So one way to look at it is you just connect it from one branch point to another branch point. And another way to look at it is just saying that you both branch point has a branch cut to infinity. Possibly. One has a branch cut, something like that. And minus one also have a branch cut. But the reason we don't draw branch cut after z greater than 1 on the y-axis is that the effect of this branch cut, these two branch cut actually make the function uh, not multi-value. You cause it, uh, it becomes not multi-value. The, the either way to look at it is fine. So connect the two branch pointers, so you have two branch cut, but the two branch cut has some cancellation somewhere to make it the branch cut, the effect of the branch cut is beyond a certain point is not important. Okay, so to see that you just like you define your domain. So for one, first you define your angle, right? And so for a certain z, for a certain z, you have the difference from -1 to 1. So you can have the difference from 1 is z minus 1. I think you can call this phi. Phi. And then z from 1 is and with a branch cut connecting the two, basically, it's like they go both going to infinity, or you can say both go to negative infinity. It doesn't matter. But this is just like you're defining the phi is greater than 0. The pi equation is also like 1. Right? So everything just work as before, but the idea is if you going around the whole branch cut from 1 minus 1 to 1, so go around a loop to here, you don't get to another branch. You because this function now you substitute this into here, the fc will be 2 minus 1 plus 1 to the 1/2 and the e to the I 5 plus theta over here. Right. So if you're going around a loop like that, both phi and theta will increase by 2 pi, right? So, so 5 plus theta will increase by 4 pi, and 4 pi over 2 is just 1. So you go back to the same value. And so this is a special case, and so it won't work if this is not the same thing. One is z minus 1/2 factor, one is 1/3 factor, then it won't work. But it, it going around will not get you back to the same function. Okay, so you can still say you can cut the both cut the real axis. That is fine. Okay, and so now it's a little abstract. So, but when you do integration, we'll have many practice later. Then it becomes apparent how you use a point cut to evaluate integral. Okay. Any question up to here? So these all this about branch point and branch cut. Okay. Yeah.
So for the case of f of z equal to z/2, this one. So we went this way. So how are you getting the force, for example?
Going to.
We went up to this half, raised to half, then the exponential I. So let's say, for example,
Okay. Just like here, right? That's how you get to here. You said how do you get to here?
for example, if you have to look for force in that kind of situation, I see the force singularities have force and force.
Pose is not generally is nothing. It's not multi-value. These are not poles. These are not. I mean, 0 - 1/2 is also okay. C0 is still a function of this function, right? But it's singular, but then it's not a pole. Uh, so so we consider it a branch because it's not single well around this point. So the previous treatment will not work. They wanted to have this point 0 is here. You want to define an annular region to get a Lorentz series, but it doesn't work because it becomes multi-value, right? Especially when it becomes multi-value. If you redefine your function with a branch cut, then your price to pay for this is the function will be discontinuous. Say theta is 0 here, theta is 2 pi here. The function has a jump. You go around, define your function like that, go from 0 to 2 pi, it has a jump. Then obviously this you cannot use a series expansion to represent it because series expansion doesn't have a jump. You will never be able to find a series that represents a jump over here. So you cannot find a Lorentz series for this kind of situation because of the multi-value situation. It's okay. So we need to treat the branch point separately from poles. And well, pole, if it is not the fractional power, if this power is either -5, something like that, then we can define it. Lorentz series over here. It's not multi-value. Okay. All right. Okay.